your brain loves anything silly. And your brain likes anything you've got to actively do. So give it a try. If you act it out, let's see if you actually remember it better. Happy with that? So we've got a system whereby we can act out everything to do with what we do, just to help us remember it. So are we ready to give it a go with momentum? Okay, are we all ready? Are we ready to be silly and act it out? Okay. And you're going to learn a whole sign language, but it's so easy. Okay. What do we say if something's a vector? We say it's a V. Okay, everybody, momentum is a vector. Let's see everybody's hand. Vector. Okay. If it's a vector, it's got a direction that is positive. So let's choose, let's say that way is positive. Okay. So there's my mass, and there's the mass moving in a positive direction. So move your mass in a positive direction. I think it's going to make me dizzy if I'm going this way and you going that way. So let's all just make that way positive. So whichever direction. Okay. Now just as a thought, if you've done Newton, Newton had long hair, so there's Newton. Okay, so let's do Newton. Newton 1 says that objects that are moving will keep on moving at a constant velocity. So Newton 1, just do that everybody. Newton 1. Let's get our mass moving at a constant velocity. Okay. Now with momentum, we're going to have a second mass. Okay. That mass is going in this direction. Happy with that? What's this direction? Negative. So there's our negative side. So let's have a negative. Okay. Moving with Newton 1, constant velocity. Then they get to collide. Poof. So there's going to be a collision. That's how we'll show a collision. And then we don't know what's going to happen, but now there's a few possibilities in momentum. So there's only a few possibilities, and I'm going to tell you them. Then we're going to do a problem on them, and then you're going to get 100% for them.
Yes, sir.
The first possibility is we got this one and this one. They come together and they stick together after the collision. They may go this way, they may go that way. We've got to figure it out. Happy with that? So after the collision, just do this. And if it moves positive, we'll do that. That's positive. Or maybe this one was bigger and maybe it was negative after the collision. Do you agree that's a possibility for momentum? Yes. Great. That's possibility number 1. Or let's try possibility number 2. Okay, everyone ready? We've got a positive thing, negative, moving at a Newton 1. They collide. What do we do next? Poof. One goes one way, one goes the other way. So the one that goes this way is now positive, and the one that goes that way is now negative. So that's another possibility. They don't stick together. Happy with that?
So they change direction, swap direction.
What happens is they can swap directions. So this one bounces off this one, and this one's gone from positive to negative, this one's gone from negative to positive. Or maybe they collide and both go, but at different velocities in that direction. Either way, it's easier. It's the same class of problem. All happy with that? Okay, now here's a third possibility. And that is, we've got 2 masses. Okay, here's our 2 masses. One's heavy, one's light. And we tie this ruler, it's got holes in the bottom with a thread. We put that there and we shoot them apart. Okay? We have a string, we light the string and it shoots them apart. Let's act out the third possibility, and that's the possibility that came up in, I see, last year's paper. So I hadn't seen last year's paper, but I know it's a possibility. Should we act it out? Let's try. Okay, I haven't tried it, but let's do it. We start with two masses, and they are stationary, right? Then, what's that direction?
Positive.
Positive. Okay, then there's our poof. And this one goes positively. It doesn't matter which way you choose, so you can't be wrong. And this one goes negatively. Everyone happy? Those are the three possibilities. And then the last thing that you need, well, there's two more things that you need to know about momentum. We could look at just the one, we ignore this one, and we just look at one by itself. So we could just say this had zero momentum and it changed to having positive momentum. So if we look at just one object's change of momentum, now this is not two objects, this is one object's change of momentum. The change of momentum is called impulse. And you've got no note that says so. And let's test it further. Do you know what a change in anything is? A change in anything, do any of you know how it's defined as? So change in momentum is momentum, mass velocity, after, minus mass velocity, final. There's my F. So a change in anything is final, momentum in this case, minus initial momentum. And that is called impulse. And that's for just one object at a time we look at. So this one's impulse has changed positively, and this one's impulse has changed negatively. In every momentum problem, you're going to use a principle called, anyone know? The principle or law of conservation of momentum. Okay, so let's just act this out first. What is our symbol for momentum?
P.
Little p. Just everyone do a little p. You see, here's the upright of the p, and there in between in that little gap is the little p. Okay, there's p. What is momentum otherwise a combination of? Mass. There's the central, there's the three parts of my m. Mass times velocity. Everyone? Go on. Okay, so let's do it again. Little p equals mass times velocity. Okay, once more. Little p equals mass times velocity. Great. Gee, you guys, if physics doesn't work out, acting is definitely going to be for you. Excuse me?
Will this be a regulation in exemption?
Will this be
Will this be a regulation in exemption?
a regulation?
Bring this.
Well, if they see you doing it in the exam, hey, what's little p equal to? That someone's doing MV, and there's going to be a problem, Houston. Okay. This principle that's used to solve momentum problems is called the law of conservation of momentum. Just say that, everybody. The law of conservation of momentum. Now, if you conserve something, it means it's here to start off with, it's there to end off with. So some very smart guy, possibly Newton, discovered that if you start out with a certain amount of momentum before a collision, after the collision, if you do the sums, the momentum's the same. Doesn't sound intuitive, but someone had to discover it. Could have been, if you discovered it, your name would be on it. Well, it wouldn't be called, maybe it would be called by your name, but it's just called the law of conservation of momentum. Okay, so what is the big deal? If we've got two objects, one's got positive momentum, one's got negative, and they collide, and they end up going like this, with positive momentum both of them. If you add up the mv at the end, it's the same as the mv to start off for both of them. That's the law of conservation of momentum. So you see, I don't want you to write a note, the sun rises in the east. I want you to know, the sun rises in the east. It'd be stupid of us to say things, the sun rises in the east, objects fall down, because you know. That's how we must know our physics. So when it comes to the law of conservation of momentum, that is how you must know it. You must just, but let's give it to you. So here's the law in its totality. It's a single sentence, and I will possibly write it down. It's in a closed system. Now, a closed system is the two objects, okay? In a closed system, the total linear momentum means everything we do in metric goes in a straight line. We don't go sideways or skew. We only go left and right, north and south. We can't go northwest and northeast. So in a closed system, that means this object 1 and this mass 2. In a closed system, the total linear momentum is conserved. Will you be able to say that? But do you understand, first of all, what I mean by a closed system? If I've got 3 masses, the closed system involves 3 masses, but you won't have in the trick. If I've got 1 mass, we can't have a collision. So we can only have 2 masses. Okay, so if we have 2 masses, that's now our closed system. We're only looking at A, or number 1 and number 2. That's now your closed system. We could put a big mental fence around that. There's our closed system. In our closed system, the total linear momentum, that's if we add the positive and the negative, add it, is conserved. The total linear momentum is conserved. Does that make sense? So that if it was 5 before, what do you think it's going to be after? 5 after. If we add this one's and this one's before and it comes to 2.5, what is my answer going to be at the end? 2.5, because 2.5 is conserved. Make sense? Does this sound difficult, guys? It sounds relatively easy, don't you think? And that's momentum. Now we just got to do a few problems that involve this principle. Let's just try saying it though, everybody. Let's all say it. In a closed system, let's just show a closed system. That means including everything. In a closed system, the total, which is what closed system means, the total linear means in a straight line, momentum is still there in the closed system. Still there. I can't think of a symbol for conserved, but it's still total is total. Happy with that? Or, first thing I'm going to write on the board, or there's a way of saying it. I'll just do that. Have you seen this? The sun. Have you all seen that? The sun, what is the symbol for momentum? The sum of P. Now we've got to think of a thing for before. Initial equals. I haven't got anything for the sum of P. Final, there's my F. So, in other words, I've got to add N, first mass, 1, V, initial 1. The I initial 1 means this mass has an initial velocity. It's going to have a final velocity, okay? Plus, here's our second mass. So we have this one, here's the second one. Plus mass 2, there's a times here, right? V initial 2 equals, and the first problem that I'm going to give you is where they join together. So we say M1 plus M2 and V, there's only one final velocity, so we can call it Vf, and then we solve the problem.